Hi, everybody. I think there is one more topic I haven't touched on yet, which also belongs in our series on Raymarching technology. It's about creating arbitrary shapes using planes with various positions and rotations. So let's take a look at how we can compute the rendering of the so-called Platonic solids. So, shall we tolerate the usual introductory talk one more time? Hopefully, yes. It might be useful for those who have just discovered this video without any knowledge of the previous episodes. So, we are building on the shader we've ended up at the end of the previous part. I have it open in front of me. And if you've been following the entire series up to this point, your code should be in the same state. If not, there is of course the option to get all stages of this project from the Godot shader pack, which you can find on my Gumroad profile and which I've linked to in the description of this video. So, as I said, we'll be using planes. We actually already have one here. It's the ground, which slightly reflects all the other objects. And as you may recall, we created this plane at the very beginning of the entire series, and we did it in a very simplified way, since it's a plane passing through the origin and parallel to the x and z axis. So its formula depends only on the y coordinate of the current point P. We can take a look at it in the material SDF section function. So let's scroll down and material SDF should be right here, and here it is, ground, and we can see that instead of something SDF there is only p.y. However, this time we'll need a general plane that is tilted according to a normal vector. Fortunately, even such a function won't be too complicated. Let's add a plane SDF function before all the other SDF functions. So it's gonna be very simple. I'll scroll up and find the first SDF function, which should be here. It's the struts, and before that, let's put the code. Float plane SDF with vector3p and vector3n for the normal vector, which defines the tilt of the plane, and we simply return dot product of these two vectors p and n. That's it. Okay, and we can start creating the first solid. As we know, Platonic solids must have all faces made up of regular polygons of the same shape and size, and the same number of edges must meet at each vertex. There are exactly 5 such solids, at least in the ordinary 3-dimensional Euclidean space, which we now see in front of us. We'll start with the first one, the tetrahedron. As we know, a tetrahedron is made up of 4 equilateral triangles, so in our calculations we'll need a constant related to the internal angles of these triangles. We'll add this constant to the code, so I'll expand the area and scroll up to the constant section. It's here, const float, let's call it t for triangle, and it's 1 divided by the square root of 3. Okay, and now the function, which will have 2 parameters, the usual point P and the distance of the faces from the center of the solid, which will denote as D. Scrolling down to the SDF functions, right after the plane SDF, let's write this. Float tetrahedron SDF. And as I said, vec3p and float d. Okay, so as I said, we'll create the tetrahedron using the intersection of 4 planes. Each plane will be offset from the center by the by a certain distance, and will have a different normal vector. I won't bore you with a detailed explanation of these calculations. What matters is that they're based on the constant I wrote down a moment ago. So the individual planes look like this. Float plane 1 is plane SDF with parameters p, and now we need to offset it. Vec 3, d, just read these. And the normal vector is vector 3, and negative t, our constant, t and t. Okay, so this is the first plane, and now I'll copy and paste this 3 times and change the parameters. 1, 2, 3, and it's plane 2, plane 3, plane 4, and in this case that would be d and negative d, negative d. Now it's negative d, d, negative d, and finally negative d, negative d, d. And as for normal vectors, t, negative t, t, sorry, t, t, negative t, and negative, negative, negative. Very well. And as we know from earlier episodes, we perform the intersection using the max function. So let's return this result from the function. Return max of max plane 1, plane 2, and max plane 3, plane 4. All right. And now we can create the material definition for this tetrahedron and add it to the scene in the material SDF function, which is here. Okay, and I think we'll just copy and paste something and change the parameters. So let's, for example, copy this torus and replace it with tetrahedron. Okay, and material can be something like slight bluish. Vector, this is the diffuse color. Let's keep it as it is. This is the specular color, the material. And now 0 for the scale factor, 10 for the something, I don't know, shininess, yes. And now we need tetrahedron. SDF, and we don't use the bend function here. Let's get rid of it. Okay, and P minus, I think we should put it somewhere to the right, like we could have seen at the beginning of the video, because we'll have 5 solids and we need to find some place for them. 5, now 3 for the Y, and I think 7 for Z. Okay, and the parameter, there's only 1, and I think I set it to 0.8 and 0 and 0. Okay, what exactly is not correct? I think there are too many brackets here. Let's delete one of them. Okay, now it's perfect, and we can add it to the result. Result is union of result and tetrahedron. Okay, let's take a look at the scene here. Okay, and it seems I placed the tetrahedron more to the right, so it's not currently visible. We need to tilt the camera. So I will set the camera to, I think it was 5 and 5.5, and negative 8 is correct, and zoom, let's reset zoom to 1, and look at point should be 0 to 0. Okay, and where is it? Why don't we see it? Okay, so it's my fault and my stupidity. Sorry about that. As you can see in this tetrahedron SDF function, I wrote equals instead of minus in all 4 planes. So let's fix it. And now we can observe how the planes gradually show up. 3 and 4. There we go. Here it is, our nice tetrahedron. Perfect. And however, for these solids, it would be better if they rotated around their axis so that we can easily see them from all sides. Let's add the rotation code to the tetrahedron function, and I think we already have it here in cuboid commented out. So let's just copy and paste and wait for it. Yeah, now it's rotating and everything works as expected. Okay, so now we can clearly see that the new object is indeed a tetrahedron and it reflects nicely in the pseudo mirror right here we turned the ground into. So the next Platonic solid is the cube, which will be easy since the corresponding function is already included in our code. So let's just add the same rotation around the y-axis, and it's exactly what I've been just referring to. Let's uncomment this line in cuboid SDF function. So now both instances of cuboids are rotating as well. All right, and let's find the material SDF and we'll create the hexahedron. Copy the tetrahedron and make it a hexa. And now let's keep all the parameters as they are, and here we will use cuboid SDF, and we need to shift it to another coordinates, and I think the best position was 2 and 3 and 7. And now we need 3 parameters, of course, 3 dimensions of the cuboid, and all of them would be the same. 2, 2, 2. This is our cube, and we again need to add it to the scene. Let's copy paste and use a hexahedron right here. Okay, and if we take a look, yeah, here it is, our cube, and it's rotating just like the tetrahedron. Okay, and as I said, we can see that all the cubes are rotating, which makes sense because they share the same function. If we wanted only the new solid to rotate, we would need to create a separate function for it, similar to the cube with rounded edges. As we can see, it's not rotating, or move the rotation one level up into this material SDF function. Very well, we can continue. Next in line is the octahedron. It's made up of 8 equilateral triangles, and we could create it the same way by intersecting 8 planes. However, that would be unnecessarily complicated, because there is a much simpler solution available. Let's take a look at this image from Wikipedia. It shows the intersection of 2 tetrahedrons and even has its own name, the stellated octahedron. In the next image, we can see more clearly that the result of the intersection is indeed a regular octahedron, and we'll take advantage of that in our SDF function. So I'm scrolling up to find the tetrahedron, and let's write up the octahedron. Float octahedron SDF, again with parameters vec3b and float d, and here we simply return the intersection of 2 tetrahedrons, so it would be again the max of 2 results. Tetrahedron SDF of p and d, and the second argument is tetrahedron SDF, and this time negative p and d. Very well. And yeah, that's all. Now we can add the new lines to the material SDF function. And When we do that, we'll see the expected octahedron, which will automatically rotate because it uses the tetrahedron functions that already include the rotation around the y-axis. So I'm scrolling back to the material SDF and let's copy tetrahedron and make it octahedron. Octa. And of course, I have to change the SDF function, and we keep the parameters and change the position. Let's put it to -1 and keep the rest. Okay, and of course, we have to increase this value d. I'll shortly explain why. And so let's make it, for example, 1.5. And I'll add it to the scene right here. So it's octahedron. Okay, let's take a look. Here we go. Perfect octahedron. And as you have surely noticed, and as I mentioned, I used nearly double the value of the parameter. Here, this one, 1.5. That's because the intersection of two tetrahedrons results in an object that is half the size. So by scaling it up, we achieve a better overall appearance. So that covers the simpler solids, and two remain, the dodecahedron and the icosahedron. In these cases, there will be so many planes that we'll give ourselves a bit of help by first creating a function for so-called double plane, the intersection of two planes that are offset from each other. So let's find it here, the right section. Here it is, plane. I'll put the double plane after that. So float double plane SDF and the parameter vector 3 p. Now we need an offset, so vector 3 o and the normal vector 3 n. All right, and again we'll make the intersection, so return max of plane SDF, the first one, and this one is shifted by the offset O, P minus O and the normal vector. And the second one is plane SDF, and this time it's negative P minus O and the same normal vector N. Okay, it's not really an intersection in the strict sense because parallel planes never actually meet. It's a calculations of the space bounded by those planes, which we'll then use to make it easier to construct the final solid. And now the dodecahedron. Just like the other Platonic solids, it has a number of interesting formulas associated with it, but we won't go through them all. What do we need to know is that a useful constant this time will be the so-called golden ratio, denoted by the Greek letter phi, and its value look like this. Scrolling up to the constant section, and let's put it here. Const phi is, and it's 1 plus square root of 5, and this result is divided by 2. Okay, this is our golden, float. Now it's correct. Alright, so let's insert the SDF function. I'm scrolling down to tetrahedron, octahedron, it would be right here. Once again, I won't go into a detailed breakdown of the algorithm so the video doesn't drag on too long. In short, we use the golden ratio to compute two helper vectors, which then serve as the basis for determining the positions and distances of the planes for the subsequent intersections. And for the remaining faces, we'll use coordinate permutations of the vertices via swizzling. Like this. So float dodecahedron with SDF with parameters vec3 vec3p and again float d for the size. All right, and I think we can start with the rotation now because we would add it there at the end anyway. Okay, and now as I said, we are creating the helper vectors. Vec3v is the normalized version of vector 3, 0, 1, and our golden ratio. All right, and the second one, why it's not recognized? Because I'm an idiot, of course, capital letters, sorry, phi. Now it's correct, and the second one, vector 3w, is again the normalized version of vector 3, 0, 1, and negative golden ratio. Okay, and now what? Sorry, comma. Okay, and now the planes. Let's call them d plane, the variables, because we are working with double planes. Float d plane is their intersection of just the plane, double plane I mean, double and SDF, and the parameters p, d times v, and v. Okay, and now since we have more planes than before, I won't just call them d plane 1, d plane 2, and so on. Let's make the intersections gradually. So the second d plane is the intersection, so maximum of another double plane SDF, and this time it would be p and d times w and w, and we do it with the original d plane. So let's hope I won't make too many typos here. This is the first, this is the second, and now we need to do the swizzling, and I think I'll just copy and paste this line. And now d times v, but we will rotate the components z, x, y. This is the swizzling I was talking about, of course, dot. And the w, there is no w, there is another simple v, and z, x, y, and again with the d plane. Okay, and let's make it 3 more times. 1, 2, 3, and v, y, z, x, y, z, x, and now we'll do the same with w. W and w, x, z, y, and again w, w, and y, z, x. I know it looks terribly complicated, but in fact it's just a simple principle applied 6 times in a row and with some changes, and as a result we return the plane. So let's see if I made it right without any typos. Let's add this object to the scene. So scrolling down to the material SDF function, and I'll copy octahedron definition, and so let's make it Dodecahedron. Okay. And the function, of course, is Dodecahedron SDF, and the coordinates would be -5 on the x-axis, and let's keep the rest as it is. And finally, I'll add it to the scene. Dodecahedron. Okay, fingers crossed. Yeah, here it is. Can you see Dodecahedron with all faces are as expected. And when it rotates, we can see that it looks like it should. Very nice. And now we have the icosahedron left, which is the dual of the dodecahedron, meaning its vertices are formed by the centers of the dodecahedron faces. We'll take advantage of that in the SDF function, which once again uses double planes, the golden ratio, and the constant for equilateral triangles, and plenty of intersections. So the function will look like this, scrolling up to our SDF section here. And it's supposed to be longer, so let's hope I won't make any mistakes here either. Okay, and I'll simply copy and paste the dodecahedron SDF function, rename it to icosahedron, and delete this part. So we have a simple rotation, and then we'll return a d-plane, which is not defined yet. Okay, so this time we will need not 2, but 6 helper vertices. Vectors, let's write them up. Vec3 v1 is our t constant multiplied by vec3, and now the permutations. So first 1, 1, and 1. So this is the first one, and the others will be just variations. So 1, 2, 3, 4, 5. It's v2, v3, v4, v5, v6, and now t remains as it is, and -1, then -1 and -1. Now we have v4, -1 is the last one, and v5, and now we need already the golden ratio again, so 1 divided by phi and phi. Okay, and the last one is 1 divided by phi and -phi. Okay, and now the double planes. So float d plane is double plane SDF of P and D times V1 and V1 for the normal vector. So this is the first one, and now we'll gradually add more of them and always make an intersection using the max function. So the plane is max of double plane with P, and this time D times V2, and the normal vector is V2, and the intersection with the original D plane. Okay, so this is the second plane, and now I'll make 4 more copies of this. 1, 2, 3, 4, and we'll use the other vertices. V3, V4, V5, V6, and the same for the normal vector. V3, V4, V5, V6. Very well, and now the permutations of the vertices using the swizzling. So I will copy this line, copy this line, and make d times v5 dot zxy and v5 dot zxy. Okay, and let's do the same for the last permutation, y zx and y zx, and now let's copy and paste and do the same for v6, v6, and here V6, V6. Okay, that's supposed to be icosahedron. Now we can add it to the scene. Scrolling down to material SDF, and I'll copy Dodecahedron and rename it Icosahedron. And again, I'll keep the parameters as they are, except this one, which is supposed to be icosahedron SDF, and the position would be -11 for the x coordinate. All right, and let's add it right here, copy, paste, and rename to icosahedron. Okay, and let's show it. Something is something is wrong. At least you can see what happens if you experiment with the planes and vertices, and you can get something which looks pretty interesting, but definitely it's not a Platonic solid. It can be some kind of a gem. So let me open the function again, and I'll hopefully find the typo here. And here it is. Actually, it's in the definitions of V5 and V6. The first component is supposed to be 0, not 1, and 0. Okay, and now let's take a look. A perfect icosahedron. Now it's correct and perfect, and as we expect. Very well, so I guess we are done. Now we can admire the result and appreciate how all the objects are nicely reflected in the mirror-like ground and cast shadows. Yeah, 1, 2, 3, 4, 5, and some of them even cast shadows to other Platonic solids. Yeah, it looks very nice. Once again, thank you very much for watching, and I hope this video was at least somewhat helpful. Of course, this technique isn't limited to Platonic solids. By combining planes, we can construct practically anything as long as we are not afraid to experiment a little. In fact, that's what I just did with the icosahedron, and it wasn't planned. For example, we could create a cut diamond this way, give it the right reflectivity, and make it a beautiful addition to our scene. But that's probably something for the future. For now, take care, good luck with your projects, and see you in the next video.